Step on that.
That's it.
Okay, here's tack. Tack. Okay, hang over to me. Sweet. Check what Okay. Hands up. What time is it?
3:36.
See, what's the max distance? We take this off the edge. We're gonna be on the box.
No, gotta be on some. Well, kick it over.
Take it over, hang.
No, max distance is 11 kilos.
Okay, where's 211 though?
211 is
touching the edge.
with the outside edge and the outside edge.
Okay. It's more down. Right back.
30 seconds.
That's good.
Alright.
15 seconds.
Alright, go stand on work.
No problem.
Judges now need to measure the distance.
So the ball's over the box.
Because if you pick them up, it gets to a certain point, it flicks them into the little catcher thing, just falls in. We estimate the time counts about 6 seconds. Our device, we got the reduction gears on here approximately, I think it's in the ballpark of 3 to 1 or 1 to 3. I didn't actually do the engineering behind it. It worked pretty good on a little boat that I had, so let's try it on this. It worked pretty well. I got a little toggle switch on here, so a little crane mechanism without laying down, made it easy for time. And we use 2 4x inches in parallel here, mechanism to pick it up. But that's our device. Any questions?
How does it tip?
You'll see. What happens is we got these reach arms here. As it goes up, it catches, locks in, and this pulley, so we're still pulling it up, and it's locked in. What it does, just dumps it over.
Does your system start as soon as you put the battery in, or is there a switch?
I gotta flip the switch.
Okay. Time is okay.
Okay. Yeah. Yeah, we gotta put the new battery. Whoops. Oh, here's my answer. Timer's ready?
Yep.
Go.
New battery. Yep.
Each run gets a new battery. Okay, she'll have some nice extra batteries.
Jimmy, Mike Plumley, and the shovel. Did you get the box? You all ready to go? Tell you what to say?
Go.
What's the spray for, guys? I'm just spraying it for it. Okay. But I'm just yourself if you don't report it. That's up to the others. 2 minutes left.
One, 101 centimeters and 8 millimeters.
My name's Mike Plumley. I'm from Coast Guard Academy. Matt, Randy, and Pat helped me set up things here. My partner and I, who's not here today, he's at a crew race. We set up what we initially called a shovel. It's kind of evolved into more of a cart, whereas it's holding the balls now without touching them, and we'll carry them over. It was designed more for simplicity and reliability, so it's just going to pull the balls across and deposit them into the box, which has cotton balls in it, to stop them. It was initially designed with a shorter track, and just this week I made it longer to increase our ratio. So it's kind of my first time seeing how it's going to go like this too. So we'll see how it works. Let me say go. Ready? Go.
Go.
Okay, we got 2.9 seconds.
Here's the game plan. Hello. Next up is Brown University. But before you get started, I'm going to ask all the teams, we're going to try to minimize walking on the board if possible. We don't want to, bring the dirt from the carpet, floor, and everywhere else in your shoes. Because we got 10 teams going through here, so we want to keep the board as clean as possible for everybody. So let's minimize walking on the board. Kneeling on it is fine, but let's try and keep the shoes off of it. Is that okay with everybody? All right. I'd like to introduce Brown University, and they're faster than a speeding duck.
Thank you. My name is Greg Black. This is my colleagues Mark Schnittman and Ernest Kim, the fashion speaking duck guy here. Basically, we did some research into the ideas behind this competition. Basically, what we've got is one AA battery, and we've got a motor for actuation. So the power source from a AA battery is pretty much all we've got. So the idea is to utilize as much power as we can from that battery. Given that we only have 1.5 volts, we determined that given the mass of 2 ping pong balls and 1 golf ball, if they were, brought the full distance over the, short amount of time using all the power, if they were tossed through the air without any friction, any wind resistance, or any inertia, or in rotational inertia, then we could do it in 0.88 seconds. Unfortunately, so that's the best time anyone could ever get in the universe, given the laws of physics and such. So we didn't quite make that. So we determined that what we want to do is use battery for the entire length of time that we're running, so we get as much power as we can. And we also want to do it such that, the balls are moving while it's going. So, what our plan was to compress the spring and launch it. Those two things, launches the balls and also starts compressing the spring using the motor. That way, during the run, as the balls are running down, the spring is also being compressed. So we're moving the balls and doing work at the same time. And it worked pretty well for us. What we got is a battery attached to a motor and attached to a gearbox, courtesy of Lego. The gearbox utilizes worm gears, which are very efficient and tend to, give great ratios. We've got I think it's a 200-to-1 ratio, as well as a special cam pulley system that changes its radius as it turns. So we get, because it's not a completely linear spring, it's easier to pull at the beginning than it is at the end. So as it turns, the radius of the moving arm basically shortens, so it gives us the electric power that way. We utilize some tracks, and basically we pull them together, get the golf ball shooting down, and because the ping pong balls are hard to push along, we're giving an impulse that's got a lot of air resistance and they're really light, we put them in front of the golf ball, and that way the golf ball moving along helps them up behind the box. Can we move these boxes before we start? Can we move the balls? Yeah, that's gonna move that. So, yeah.
Ready, set, go.
One thing you guys should be aware of for your next round.
Okay, you tell me. Okay. Oh shit. Ready, set, go.
You know, we're going to call this a blank prototype.
Non, c'est parce que j'ai mon nez qui est derrière, par contre on me colle dessus, je mets le nez. Non, mais c'est... Oh oui.
This is our untitled tramway transport system.
Our solution to this problem is to build a tramway system that would carry balls from one end to the other end, using just the strength to reduce friction, and a car can carry it, just like an ordinary tramway system would, except for the fact that the system is not pulled across. What we did instead is we used the motor to build an advantage for us where we could actually roll it from one end to the other. The motor will tighten the string, creating an incline from one pole to the other, pick up the cart, and it will roll in deposit the balls into the box, and then remain locked in the box right there. Mike's going to explain to you how the motor functions to create a sync on.
We're given the 1.5 volt DC motor to work with, and we knew that in our system we wanted to develop a lot of potential energy by lifting that thing up and letting it roll down using gravity as our workaholic there. So what we did was we used precision 601 gear head on our motor assembly, and this gear head gives us an output of almost 1.5 foot-pounds of torque as compared to the 0.48 ounce inches that are provided by the motor by itself. So with that amount of torque, we apply that to our cable through a Bowman arm, which is this aluminum rod here. What this does is when we initiate the system, what happens is the rod rotates through about 45 degrees and applies some tension into the cable that allows the trams to roll down the cable on a precision ball bearing pulley and deposit the balls in the box. And the way that we actually deposit the balls into the box is with a string activated release mechanism. And what this does is as the tram reaches the front edge of the box, it pulls a release clasp, which allows the bottom of the tram to swing open, depositing the balls onto our duct tape kind of adhesive catching mechanism, hopefully to reduce the explosion of the balls once in the box. So that's how it works, and we've actually achieved run times of 2 seconds. Of course, due to human error, that may not be achieved here today, but we'll see what happens. Getting the battery? No, that's fine. All set. Go. What? Go. Come on, set. Go.
Long for some just.
That was a good job, guys. All right. Okay. So last guy in place. Project called Rescue Me to get the balls from one end to the other.
Gonna check the spring, it's still going. What do you do? That would be a freshman. The problem is, this is called rescue me because I'm a freshman and the seniors built it. Tanya happens to be a senior. He's going to help me put this together. It was actually built by Owen Kramer and Brian Andreeski and a couple other guys, I'm told. I originally started working on this to get it prepared to final touches. This is a hardened steel rod. There's a precision linear bearing. It slides. The idea is, hopefully anyway, slides smoothly just along here while being pulled by a string. And it won't come on edge. Sorry. The string will pull this apparatus to the end while being connected at this end by this string. The string pulls this little wire frame here holding the balls, and by the time it hits the end, it should be torn. It should drop on balls and hopefully that's it.
Is that a telescoping steel rod?
No, these are all screwed in together.
It's not in a hole back here.
Before you touch it.
Yeah.
Okay. Yeah, I was just maybe one person to do that.
Go.
I didn't touch it. Sorry.
Ready? Go.
Hook it on the...
Battery out. The base handle. That's been a long way of trying to bear with us here. Wait, you got that battery out? Sure.
Okay, get ready? Set. Go. Set. Go.
Jim.
Alright, moving right along. Next team up is from the University of Maine, four-man team, and I'll let them introduce themselves when they do their presentation. Their project is the Impactor.
Guys ready? Set. Go.
I would just suggest that you do the level in your boxes instead of those big boxes. Make sure that you
highlights, right?
Good, eh? Yeah, everything's set. My group members are Jim Belstrade, Michael Rosenzell, Benjamin Blanchett. We're all juniors at the University of Maine. We originally built this project for a class last semester. We went through a couple different designs. Originally we had a system that operated on potential energy, and we found that we could do it in a faster way. So we started thinking about having some type of system where we could return the energy as the balls moving down the track and kind of have an impulse system so the impact would be formed. A couple different times with a pusher plate. We initially had some linear bearings and we had the shaft attached to the pusher plate. We found the linear bearings, even though they're costly, we originally thought that they'd do the job pretty well, but as it turned out, a 24-10 nylon bushing works about 10 times better as far as friction is concerned. So once we got rid of the steel shaft, we started thinking ways to lighten up our pusher plate and try to get all of our energy from our rubber band into the pusher plate, and actually, so that way more energy would be transmitted through the balls and into the bodies. We have a steel base, kind of to weight everything down, plexiglass legs, just kind of for looks. And the gear mechanism is actually out of the whole remote control car with the winch assembly. We got inside there and kind of did some reworking with the gears, and we have about 8 gears there. Like I said, Jared's going to flick the switch, the balls will move down the track, and the pusher plate's going to return in the same amount of time. And that's about it. Any questions? All right.
Ready? Get ready? Get set? Go! Okay, you guys ready? Set. Go!
Put them in your approximate position. Everybody else. Alright, when the team moves, we'll get to that. So when you're ready to start, what I do
Okay, first of all, my name is Jean-Luc. My partner is Jean-Philippe. We think two main principles. We wanted to maximize the use of the battery, and after that to minimize the losses, transporting the 3 balls from one box to another. Okay, to make sure that we reduce any rolling, we wanted to minimize the rolling resistance using kind of a track and not steel, but aluminum wheel. Aluminum just because we wanted to get the maximum static friction coefficient. At the start, we put some silicone on the track to also increase the static friction to make sure that the wheel didn't spin. Okay, and that's for the losses of by friction. After that, we wanted to maximize the use of the battery, that it's limited to 1.5 volts, but the motor can work, it says to 3 volts, I think. But we create a kind of electronic mechanism that that we could assimilate to a mechanical system. That would be kind of a variable radius pulley. Okay? Because at the beginning the motor can deliver a lot of torque, but it is not spinning, so there is no power delivered. At the end, the engine is spinning, but giving no torque. So this gives us a kind of a bell power shape, and we wanted to keep it the use of the engine at the top of the bell. Okay. Okay, so the sequence of the system. Just after we put the switch on, the vehicle pushed the ball into the small net, and after take the net with the little arms here, transporting it to some other leather pocket down there to minimize the ball moving. So think that. With the capacitors, we put a 1000 ohm resistance to make sure that the capacitors are empty. So after 10 seconds, just after the last try, the capacitors are empty.
Ready?
Yep.
1, 2, 3, and go. Yeah, 1, 2, 3, go. One, 2, 3, go. 1, 2, 3, go.
Mona Muscati and Robert O'Neill, and they have the project formerly known as the project.
Hi, I'm Robert O'Neill. Yeah, actually, our project just has a symbol for it, so it's a little unpronounceable. Look at the programs, though. This is Mona Muscati, and we're going to set up our project and then talk about it.
Yeah, that's good. Ready.
They'll put it on until the spring. Warn me before you turn it again.
Well, I thought I was better.
Oh, okay. Well, don't worry about What we looked at is a similar design to some of the other ones we've already seen. As far as using the overhead line or a single rod connecting the two. Originally, we tried to use a precision rod and linear bearings going to flow straight across, but we found it was a lot easier to use a line and fit it in the box. We wouldn't have problems with taking up space that way. But in order to use the line, though, since it wasn't rigid, we had to figure out a way of providing enough tension in it. And so that's why we came up with a system of counterweights. Provide enough tension in the line, because we didn't want the line to sag in the middle, otherwise for the second half of the run it would be going uphill and slow us down a little. And any questions about the stuff you see before you? Okay, now let's get the battery.
202.
Just that. Okay.
You want to toggle the switch?
I would put that switch up on haptic a little bit. And actually,
Oh, yeah. That's down.
just
Okay.
Should we take it down and make sure it doesn't fall off?
Why don't I do
Or?
that?
Okay.
Set, go. Front floor.
Ready, get set, go.
Yeah, I'll for the first stroke.
Going to be from you, Matt Jarvis. You by yourself? You got I'm done with the locomotion.
All right, did everything. Just
Set, go.
I guess I better hurry up. This is my design. Obviously, with limited power, you want to move as little mass as possible. I built cages for the balls. They're made out of soda bottles. I cut pieces of soda bottle and got a wooden ball from a craft store and shrunk it around. And there's an 8-inch clearance all around. I have a take-up spool that just winds the string up. I played with different widths of the spool because the string wrapping on itself constantly increases the velocity as the radius gets bigger. And so I'm trying to constantly accelerate the balls, and I play with the width of that to get the best time. I have a trap here, which is just a tapered trap. And the balls actually get accelerated and driven right into a wedge-shaped area. Underneath the bottom here is a piece of soft foam. So they compress the foam and just jam themselves in. And then it locks up the motor. No.
Okay.
What else can I say?
It looks good. Now when you're ready. Set.
Take the timer.
1.8 seconds.
Yeah!
Ready, get set, go. 1.7 seconds.
Wow! All right, everybody listen up. You know, this is going to be the last one. And then after this, we're going to do this awards right in here, so don't go anywhere. You know, let's keep the program moving along real good. And we want to keep it that way. So after this run, we're going to do the awards. Then we're going to head on over to dinner right after that.
Alright, you gotta switch this around. I got there's some points on the other side. Switch it around this way. Here, saying that I'm running anything.
That's what we meant. Yes, I can make
These Kiss 'em, a couple people didn't know what it was. It's Keep It Simple, Stupid Man. Me and one of my friends, Stan, he did make it, put this together. And basically we just saw, the quickest way between 2 points is a straight line. So, make a bridge and just yank these guys across there and see what happens. The bag's a new modification. We just made that last night just to make sure there's nothing will be touching it. So it's kind of a fun thing here. Remember this. But we get a battery. No battery. Turn over here for watching. Bounce around. Oh, shit.
It sounds like that. It's alright, I just, the battery just came off it's fine. Well, that's good. I think it'll be alright.
Whenever you're ready.
Get ready, set, go. Oops. Ready, set, go.